And so another truth table example. Let's construct the truth table for, let's see, what should we do? How about A naught or B or C if and only if B implies C. Actually, I don't need that there. So by operator precedent, the negation comes first, and then you have these. Let's put a B naught here, just for kicks. So this disjunction comes after the negation. This disjunction and this implication are calculated, and then the final connector is this one, right, by operator precedence. So we've got three propositional variables here. All right, three propositional variables. So the truth table has 2 to the third equal to 8 rows. Okay, so alright, so that's 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 7, one more. So we need 8 rows, and the three propositional variables are A, B, C. And we want to write down, first thing, all possible truth value combinations for A, B, and C. And that can be accomplished by taking the first column and going 4 true, 4 false. Next column, alternating 2 true, 2 false, 2 true, 2 false, true, true, false, false. And then the third column as such. Okay, so that gives you all possible truth value combinations for the three variables. And now we start putting together the connectors in the order that is specified by parenthetical expressions or by operator precedence. So first would come these negations, the A naught and the B naught. So these have the opposite truth values of what is being negated. And false, false, true, true, false, false, true, true. Next, let's do this disjunction. A naught or B or C. Now, disjunction and conjunction are the only connectors of the bunch where you can do more than 2 at the same time. It's well defined for 3. In other words, A or B or C is logically equivalent to A or B or C. I mean, strictly speaking, you got to do them 2 at a time. So you can do A or B first and then do the disjunction with C, or do B or C first and then the disjunction with A, but they're logically equivalent to each other. So in a sense, you don't need to specify. in what order they happen. Just like with addition and multiplication, they're associative operations. Okay, so this is false when what? When is A not or B or C false? When
It would be when all of them are false.
When all of them are false, which only happens right there. Right? In every other row, A naught, B, and C, among A naught, B, and C, one of them is true. At least one. So the only time it's false is here, true everywhere else. All right, B naught implies C. So that's false when what? The hypothesis is true, which is right there in these rows, and the conclusion is when the hypothesis is true and the conclusion is
True.
that's true in that case. When is it false? When the hypothesis is true and the conclusion is
False.
false, right? So that would be in this row here, and also in this row here. So in all other rows, what's the case? What's the case in all other rows for B implies C?
True.
It's true. What happens when the hypothesis is false? What about these cases where the hypothesis is false?
It would be true because the conclusion doesn't matter.
Right, exactly. The hypothesis is false makes the implication true. Counterintuitive, but that's the convention, and we'll see a reason for that in a little while. So then the last column is just the full statement here with the last connector, A naught or B or C, if and only if B naught implies C. And this is true when the logical values are the same and false when the logical values are false. So true, 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 false. Okay? In particular, when they're both false, it's true. Okay? It's logically equivalent is equality of logical value. Okay, so the only time we have the statement being false is down here in the last row. All right. Is anyone confused, setup, or whatever else?
No, that makes sense.
Okay, anybody? All right. If you have questions later, it's fine. You can. I mean, later is a different day. It's fine. We'll talk about it again. Okay. So last time we left off here with tautologies. So a propositional logic statement, which is always true, okay, that is known to be a tautology. Okay? A propositional logic statement is always true, like this one. That's a tautology. And how do you see that it's a tautology? Well, you see it's a tautology by just looking at the truth table. The column for that statement in the truth table is always true. So this one's a tautology. A naught and B implies B or A. This one is not, because it's not always true. So tautology is always true. So not a tautology is not always true, but not always true means sometimes false, not always false. The negation of always is sometimes, rather than the negation of always being never. Right? I mean, someone could say, You know, you're talking to someone, or you're talking to your parent, or you're talking to your child, and they say, "Well, you always say that." No, I don't. No, I don't. I don't always say that. It means, well, you know, sometimes I say it, but sometimes I don't. Not that I never say it. Okay. So here are some known tautologies, and they're all tautological equivalences. So they're all logical equivalences. There are some that are not, but for our purposes, we're gonna be just working with these. I mean, it's a course in proof, not really in logic. So you know, we're just covering some basics of logic. Certainly, the dive goes a lot deeper than this, for sure. So some well-known tautology. So the implication tautology. A implies B is logically equivalent to A not or B. Right? Like I was saying before, I mean, one way to say disjunction, P or Q, is, well, if you don't have P, then you must have Q. Right? You know, in English, we typically mean that. Right? And that requires that the hypothesis being false makes the implication true. Because when the hypothesis is false, this is true. And in a disjunction, right, if one of the terms is true, it doesn't matter what's going on with the other one. If one of the terms is true, then the disjunction is true. So in an implication, if the hypothesis is false, then the implication is true. So this requires that convention about hypothesis being false, makes the implication true. The conclusion is irrelevant. All right, implication, contrapositive, double implication. Someone mentioned this last time. Is that A implies B is, oops, I don't need that. A implies B is logically equivalent, or no, A if and only if B, yeah, I do need the parentheses there. A if and only if B is logically equivalent to A implies B, and B implies A. Hence, the term double implication. Okay, so logical equivalence is equivalent to implication in both directions. Okay. So A if and only if B is the same as A implies B. B implies A. This is important. We're going to talk about this a lot during the semester. Right. What's next? Associativity. We already talked about that. So associativity is that A or B or C, with parentheses here, is logically equivalent to A or B or C. Same thing with conjunction. And this is only with conjunction and disjunction. It doesn't work with the other ones. Okay? Now, all of these tautologies, they all require proof. You actually have to prove all of them. So we're not going to. I mean, some of them are just like really obvious. But yeah, we'll do a couple. Associativity. Okay, so here this one is totally obvious. Commutativity. A or B is logically equivalent to B or A, and A and B is logically equivalent to B and A. I mean, conjunction, disjunction, doesn't matter in what order you present the terms. Double negation. A not is logically equivalent to A. So here's something that, you know, where propositional logic really doesn't mean the same thing as it does in English. Right? I mean, if you negate a propositional logic statement, it flips the truth value. So then if you negate it again, it flips it back. So it's the same thing as what A originally was, same truth value. For sure. But is that what double negation means in English? Or any other language that I know of, anyway? I mean, you know, your English teacher probably always said, well, don't use a double negative or whatnot. But we do. When we talk, we often use double negatives. And what does it mean? You know, so you go to the store, you know, you ask the... you guys ever saw this duck video? You know, so the duck walked up to the lemonade stand, and he said to the man running the stand, do you have any grapes? And the guy says, no. And then the duck comes back the next day. The duck walks up to the lemonade stand, and he asks the man running the stand, do you have any grapes? And the guy says, no. You know, so I mean, if the duck comes back again, the guy might say, no, I don't have no grapes. Something like that. I don't have no grapes. What does he mean by that?
Does it mean he doesn't have any grapes?
It just simply means I don't have any grapes. It's just adding emphasis. It's adding emphasis to the negative. Right? I mean, if someone uses a double negative, you know, and then their English teacher tells them not to, I mean, what he means or she means is that, you know, we're emphasizing the negative. Typically. I mean, we're emphasizing the negative aspect of the, you know, of what we're saying. So anyway, so there are some differences in, you know, in the way we sort of use speech and with propositional logic, and this is really a nice example of it. Double negation. What's next? Let's say, oh, distribution. This is a nice one. Distribution. So A and B or C. So conjunction and then disjunction, where, you know, the disjunction comes first. Remember, you can't write A and B or C. That's ambiguous. Okay, because neither disjunction nor conjunction has precedence over the other. Okay, but when you do write it correctly, you know, with showing which precedence you're talking about, it's the same as this. It's the same as A and B or A and C. So conjunction distributes over disjunction and the other way around. A or B and C is actually equivalent to A or B and A or C. Distribution. We'll do a proof of that, I think. Double negation, commutativity, De Morgan. De Morgan's laws. A and B. Now, if you want to negate A and B, it's A naught or B naught. And if you want to negate A or B, it's A naught and B naught. And this is the neither nor construction in English. So, you know, for example, I mean, if do you have grapes or apples? Do you have grapes or apples? Well, if it's not true, I do not have grapes or apples. You would say I neither have grapes nor do I have apples. Right? I neither have grapes nor apples. It means I don't have grapes and I don't have apples, which is the negation of grapes or apples. Neither grapes nor apples. Right? So, I mean, if you want to say, maybe we'll do a truth table for this. But I mean, that's the Morgan's laws there. But that I'm trying to say that it's somehow something that should be clear. But we'll do a truth table for that one. Maybe that and distribution. De Morgan's laws, complementation. Complementation is the following. A and A naught is logically equivalent to 0, where 0 means something that's false. So 0 means false, and 1 means true. So A and A naught, that's just simply false all the time. And in this context, you use a 0 rather than an F. And then A or A naught, that's just 1, that's true. So that's complementation. Identity. A and something that's true is logically equivalent to A. A or something that's false is logically equivalent to A. And then annihilation is A or 1, that's logically equivalent to 1, and A and 0, that's logically equivalent to 0. And then the last one is called idempotent, and this one is going to be used in the homework, actually. Idempotent. A and A is logically equivalent to A, and B or A or A is logically equivalent to A. Make that into Alright, trying to think if there's any other ones I should mention. So let's do a proof of each of these named tautologies can actually be shown to be a tautology by constructing a truth table. So, for example, let's do truth table for A and B or C, logically equivalent to A and B or A and C. Alright, so we need an 8-row truth table. I'll do a copy and paste from over here. Alright, get rid of those two. Alright, so the first connections that we should make are what? B or C, A and B, A and C. So B or C, A and B, A and C. All right, B or C, that's false where? In which rows? B or C, where is that false?
The rows where B and C are both false.
All right, which is this row here, and this row here, and that's it. A and B, that's true only when A and B are both true, and that's here and here, and false everywhere else. A and C, that's true only when A and C are both true, which is here and here, and then false everywhere else. Next, we want to do what? So I did this connector, this connector, this connector. Next, we want to do what? All right, this right here, A and B or C, as well as this one, A and B, or A and C. All right, so A and B or C. So that's true when both A and B or C are both true. So that's in row 1. Any other rows? Row 2. And also row 3. In row 4, B or C is false. And then in rows 5, 6, 7, and 8, A is false. So it's false in rows 4 through 8. A and B or A and C. So that's true when this is true or this is true, which happens in row 1, row 2, and row 3. And they're both false in rows 4 through 8. So as you can see, these guys have the same truth values in each row. So for in each column, sorry, yeah, these two columns have the same truth value in each row. So the final column for logical equivalence is going to give us all true, because they have the same logical value always. Okay, so that's tautology. The distribution tautology, this version of it, A and B or C. There's also the A or B and C, but very, very similar. Let's do one of the De Morgan's laws. So here's another example. So A or B not logically equivalent to A not and B not. So here the truth table only needs 4 rows. Because there's only 2 propositional variables. So the combinations are like this. We also need the negation, A naught, which is going to be false, false, true, true, and the negation B naught, false, true, false, true. We need A or B. True, 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 false. A or B not. A or B not has the opposite truth value as these. True, 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 false. Becomes false, 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 true. And then A naught and B naught, well, that's true only when A naught and B naught are both true, which is just in the last row here. And then in all the other rows, one or the other is false. So we get that. So as you can see, the two columns for the sides of this logical equivalence always have the same truth value. So this is a tautology. Okay? All right. Using these tautologies, these named tautologies, one can actually construct more tautologies from them. Sort of larger. Think of these tautologies as algebraic rules for a new type of algebra. Called Boolean algebra. Right, I mean, you've been dealing with the algebra or arithmetic of real numbers for a long time now. Man, but that's not the only one around. There's also this one, and this one is called Boolean algebra. It just has different algebraic rules that go along with it. So, for example, let me make sure I don't do the one that I assigned for homework. The two that I assigned for, okay, so this one, that's a good one, and that one, A or A and B or A and B naught is logically equivalent to A. Yeah, of course. Well, there's the one. We got to start off with an easier one. Okay, so show that the following is a tautology. Without using a truth table. So this is going to be A not or A implies B not or A or B. That this is logically equivalent to 1. Okay, we want to show that this is a tautology, okay, without actually using a truth table. Okay, what we want to do is we want to use these tautologies that have names, as algebraic rules to basically simplify this expression to 1. Okay, so there's a couple different lessons here in what I'm trying to teach at this point. Number one is to get used to what these logical operations are. So there's the Boolean algebra itself, or the algebra of propositional logic itself that I'm aiming for here. But the other thing is one habit that you're gonna have to sort of get over is, and I don't know why it's still done in high school, but um, you all took trigonometry or pre-calculus at some point, and you had these trigonometric identities that you often tried to prove, right? And to prove these trigonometric identities, you would often stack things. Like you're trying to prove that A was equal to B. Right? So you're asked if A was equal to B. Is A equal to B? Well, you say, well, if A is equal to B, then like C would be equal to D. Because A was equal to C and B was equal to D because of some other trigonometric identity. And then, well, E was equal to F because C was equal to E and D was equal to F, via some trigonometric identity. And then you got them down to the same thing, G equal to G, right? So these are all in question, but then this is trivially true because they're actually the same. Something like that. That's not the right way to do things, really. Especially when you're dealing with inequalities. What you must do is work not in a stack of equations, more so, but in a string of equalities. And that's something we got to get used to because that's really the way math is actually written for the most part. You stack equations when you're trying to solve an equation. Here's an equation, let's solve it. That's when you start stacking things. When you're just evaluating expressions, you go in a string from left to right. So let's start on that. Okay. So let's start with the left. And I want to show it's logically equivalent to something else, and then work my way down to 1. So first thing I want to do is I want to use that implication tautology. Okay, so this, via the implication tautology, turns this into what? So A implies B becomes what? Do you remember the implication tautology? It changed an implication into
A not or B.
Right, into a disjunction. A implies B is logically equivalent to A not or B. So in that logical statement downstairs, the A implies B can be turned into A not or B. One moment, guys. Okay. So A implies B became A not or B. Now I've got the negation on top of the or. I've got the negation on top of the or. So I can do what with that? I can use, remember what that one was called?
I think you might still be muted or my audio is not working.
Oh, I'm so sorry. Sorry about that. So we use the implication tautology to change A implies B to A not or B. But now I have the negation over the parenthetical expression that is a disjunction. So negation over the disjunction. And with that, we can use what? Remember what it was called here? De Morgan's laws. Right? A or B negated is A naught and B naught. Okay, but I'm also going to use here double negation. I'm also going to use the double negation. Okay, so A naught or B negated, so via De Morgan plus double negation, this is A naught and then what does it become now? here. A naught naught, which is just A. And then this or becomes and the B becomes B naught.
B naught.
Yeah. Or, whoops, I think I have, did I change something? This was an or, I'm sorry. B naught, and then or B. Okay, so that was De Morgan in double negation. A, right, we have A naught or B, and we negated that. So that becomes A naught, naught, and B. A naught or B naught becomes A naught, naught, or sorry, and B naught. But the A naught, naught is just A. All right. Next, I want to use distribution. Notice that we have a disjunction of three terms here. This one, or this one, or this one, right? This one, disjunction, this one, disjunction, this one. Before I use the distribution, what I would really like to do actually would be to put a parentheses around this. So I'm just going to do that and call that associativity. Right, just to put a parentheses around that so I can keep track of what I'm doing. Sometimes the parentheses are a good thing. Now I want to use distribution. So right, distribution was that P or Q and R, like that. P or Q and R becomes P or Q and P or R. P or Q and P or R. So that's what I've got here. So this becomes A naught or A and A naught or B. Or B. Or B naught. A naught or B naught. And then or B outside here. A naught or A, that is 1, and that was called complementation. Complement. So this becomes 1 and A naught or B naught. Or B. And then 1 and whatever, that was the identity tautology. 1 and whatever was just that thing back. So this becomes A naught or B naught or B. Right? 1 and P was just logically equivalent to P. So here I've got 1 and this thing here. So it's just P. Right, so I get that thing back. And then I'm going to use associativity again. A naught or B naught or B. I'm going to write that as A naught or B naught or B. And then B naught or B, again, is 1. And then annihilation, A naught or 1 is 1. Okay, so this is, I mean, it might look a little alien at first, but you know, when you start doing it, it should feel very familiar to you because it's just algebra again. You're doing the same kind of algebra that you've been doing all along throughout, you know, grade school, middle school, and high school. Algebra or arithmetic. It's the same thing. The rules are just a little different. And what are the rules? Well, the rules have names. There's these things here. But then again, it's propositional logic as well, so it's you know, it's got some neat interpretations to it. So on the homework, so now we've done examples of what you need to do here for number 3. So in number 3, you've got these 2 problems here. We'll do some more next time, some more examples of this to get you going. But give these guys a go. So now we've covered all the material for problem number 1 and all the material for problem number 3. So now we just need to make our way over to 2 and 4 here, and then we'll take care of chapter 1 here. Actually, I don't know, we're further ahead than I thought we were. I better keep the due date for the homework assignment the same, because if we change it to Friday, 2 weeks. No, we better keep it the same. It'll be too far out, otherwise it'll slow us down too much. Well, we'll see next time. Maybe we'll change it, but still do on Wednesday the 27th. So, okay. So for the last part of chapter 1, let's talk about translating English to propositional logic. So, for example, so what you want to do is, you want to write a propositional logic statement with the same truth value as an English language statement. So, for example, here's a few propositions, and we'll start hooking them together. H equals the horse is strong. K equals the knight will win. And or not, horse is strong. Horse is fresh. A is the armor is strong. So we've got these 3 propositions here, and we're going to hook them together and put them together in sentences, and then translate these to propositional logic. So if the horse is fresh, then the knight will win. So what's a propositional logic statement that is equivalent to this statement? Using H, K, and A. Well, you don't need A, actually, but just using H and K. If the horse is fresh, then the knight will win.
Is it H implies K?
H implies K. All right, that's the standard, one of the 2 standard ways in which implication is written, as an if-then, if H, then K, or H implies K. B. The knight will win only if the horse is fresh. The knight will win only if the Horse is fresh. Well, this is again an implication, about fresh horses and knights winning. Oh, I'm sorry, it's 117. Think about this for next time. So compare this containment, knight contained in horse, and horse contained in knight. And look at something in the gap here. Right, this is knight fought knight losing and horse fresh. This is knight winning, but the horse isn't fresh. Which one is against this statement? Which one contradicts this? And then that's the wrong one. Okay, so we'll do that on Monday. All right. Have a good weekend, guys. If any questions, comments, or concerns, or if you want to meet with me sometime outside of class, just let me know. Send me an email, okay? Or you can talk to me now.
Are we having a class meeting on Monday? No, it's Martin Luther King Day.
Oh, is it Martin Luther King Day? I'm sorry. No, Martin Luther King Day is off. I'm sorry. It's let me double check. Is it Martin Luther King Day? Monday is MLK Day is 21st. Should be on top of this. That's bad on me. Sorry. Holidays and breaks. Spring. Holidays and breaks. Oh my gosh. Ugh. Right. Huh? It is on the 18th, yes. Okay. No class on Monday, guys. I apologize. So I'll see you on Wednesday, okay? All right.
If you have time, would you mind